Welcome to New Science Practicals. My name is Mr. Mason and today we're going to be investigating gas pressure. Now the aims of this video are to explain what causes gas pressure, to describe how atmospheric pressure changes with height, and to calculate fluid pressure. So our experimental skill today, the big skill we're working on, is interpreting observations of some effects of atmospheric pressure. So our first practical I'm going to show you is going to look at the difference between atmospheric pressure and container pressure. Now this is something people get mixed up with all the time. What I've got here is a crushing bottle. Now the idea here is that there is gas inside this bottle, and this gas is hitting the walls of the bottle all the time, and each particle in that gas, when it hits the walls of the bottle, is causing a minuscule force. Now, we don't even notice those forces. They're so small. But we do notice them when we consider all the particles of the gas hitting the walls of that container at the same time. Now, if I'm telling you there's a gas in here and it's hitting the walls of the container all the time, well, why isn't this bottle exploding? Well, the reason for that is because there's an equal force on the outside from the atmosphere caused by all the gas particles all around us right now hitting this container as well. So right now these forces are balanced. The atmospheric pressure from outside and the container pressure inside, completely balanced. But we're going to do an experiment now to unbalance those forces. So the first thing I'm going to do is I've got a water bath here, or a water trough rather, and I'm going to fill this up with water. So there's our container of water ready to go. And we're going to use this because what this is going to do is it's going to create a really good seal for our container, our little bottle. I'm actually going to put a very small amount of this water into this bottle, okay? Just a small amount. So in order to help reduce the pressure in this as we heat it up. So I'm going to light the Bunsen. Okay, that's worked. So now we're ready to start increasing the energy of the particles inside, which is going to actually increase the gas pressure initially. So what I'm going to do, now before we go any further actually, some people would suggest that I should be wearing goggles at this point, but let's just have a think. I boil water all the time at home. Would I wear goggles if I was cooking at home or anything like that? Almost definitely not. So there's really no need for me to wear goggles in this instance. Now, there are safety precautions that I'm taking. I've got a heat-proof mat here. I'm not reaching over the Bunsen burner at any point. But other than that, there's really no need for me to take any additional safety precautions. So, I've got my Bunsen here. I've got my collapsing bottle right here as well. So, I'm going to change it to a blue flame so it gets nice and hot. Don't quite need that roaring flame you might have heard there. Just a nice hot flame. And turn it down just a little bit. Make sure it's all the way under. So what this is doing is I'm adding energy to the water that you saw me put inside the bottle. And as I add energy, the water's going to first heat up. It's then going to boil and change into a gas state. And now, once it's a gas, it's then going to start increasing the pressure inside the bottle. So the gas pressure inside is going to increase. But, crucially, I've left the lid off. I have got a lid here, but I've left them off. And the reason for that is because we talked about that equilibrium, that balancing of the atmospheric and the container pressures before. Well, as I heat it, all of the increased pressure gas is now going to leave the bottle. It's going to escape. And then once it's left, the pressure is still going to be balanced. The container is not going to collapse or change in size at any point now because the container pressure and the atmospheric pressure will be balanced. They still are going to be balanced. But what we're going to see is I'm going to very rapidly reduce the container pressure, reduce the pressure inside the container, and we're going to see what the atmospheric pressure does to the container. So at this point, I'm going to stop the video and I'm going to finish heating this, and then when we come back, we'll be ready to go. Okay, so this has been going now for a couple of minutes, and you can see the steam coming out of it. We've heated it to such a degree that the water you saw me add before has now boiled, like I said it would, and it's now leaving. This means that the pressures are still balanced, but there are going to be fewer gas particles inside the container. Which means if we can rapidly cool those gas particles down, not even rapidly, if we can just cool them down without any new particles getting in, the pressure will drop. Okay, so I'm going to give it a little bit longer. So just want to make sure we've got as much steam out of there as possible so that we see a really good result here. Okay, so I've now driven off almost all of the steam and almost all the air inside. So we've got a very small amount of gas inside the container. So I'm going to give this a go now. And what I'm going to do, I'm going to pick it up with these tongs. So I'm using tongs, safety point. And then I'm going to submerge the end of it in the water. Now the water is going to act as a seal here to stop any new gas getting inside. Then as the gas cools down, we will see what the atmosphere does to our container. Just going to safety first. Just going to remove the Bunsen burner. Okay. So here's our can now. So what just happened was the low, or the room pressure gas inside the container cooled down. And that just happens naturally. That happens normally all the time. But because it was submerged in the water, no new gas could get inside to balance the atmospheric pressure outside of the container. What this meant was that the atmospheric pressure, the force exerted by the atmosphere on us all the time, suddenly was greater than the container pressure pushing outwards against the inside of the walls. This meant that because the force outside the container was bigger than the force inside, the walls of the container were squashed until it reached that equilibrium point again. Now, some of you might be wondering, why can I not, if the atmosphere is pressing on us all the time with this gas pressure, this atmospheric pressure, why can I not feel it? Well, the reason for that is because we have evolved, us organisms, we've evolved here on Earth in this pressure. So our bodies are adapted to it. But this pressure is actually equivalent to about the same weight as a small car pushing on us all the time. I'm now going to show you another demonstration with some syringes. And with these syringes, what I'm going to show you is how strong the gas pressure is as I exert force on it. So what I've got here are 5 different syringes. I've got 2 which are joined together like this. I've got 3 with sealed ends, and we're going to look at the different the effect of me exerting force onto these sealed syringes and this combined system. So first up, I'm going to start with 2 of these sealed syringes. So what I've got here is just a small syringe, and as I exert pressure on it, because the gas can't escape from the end, there comes a point when I can't squash it anymore. Okay, that's kind of my limit. Now, some of you guys will probably be thinking, oh, Mr. Mason, I can definitely exert more force on that than you. I'm much stronger than you. You probably are. I'm a bit of a weakling. But the point of this is to show that actually, even though the gas doesn't appear to be exerting force, we don't think about the gas around us pushing on us at all. When we compress them, it comes to a certain point where we can't compress them any further. With this one, this is a nice little setup, because what I've got here is 2 syringes. I'm just going to have to take the end of this one. Okay, now I've got it set up this way. So what I can do now is I can quite easily go, if I push this end, we see the other end coming out. If I push this end, the other end rises. Now, the nice thing about this setup is that this is showing about the gas pressure equilibrium. Whereas before, with this one, we were kind of changing that point of equilibrium, the point where I can exert force on it, and that's as far as I can get it to go in, and the gas pressure this way is balancing my force that way. What this one's showing is it's working against atmospheric pressure again, and this one will move out until the gas pressure here balances it atmospheric pressure on the end of here. Now watch what happens if I hold one end on. Suddenly I'm balancing the pressure of my two thumbs. So the thing about this is that now I'm changing what I'm working against. So here they're in equilibrium, this one's moving out again. So that's a really key word for us today, this word equilibrium, this point where gas pressures are balanced.